Wet again? Yeah, it just keeps raining, doesn't it? So, a couple announcements on the board. I added a couple more grades to Campus Web. You might want to check those. I do have a lab upstairs for the water lab that has no name on it. So if you are missing that score, you should come up and check to see if that is yours. And we would love to give you those points. Okay? So, other things, there is a lab quiz for next week, video, link to it, handout, and PowerPoint slide in coursework. So please answer those before you come to lab so you read the handout. Cool? We're going to do a titration, and titrations are fun. We're going to use it to determine the molecular weight of an unknown acid. And so this is a classic technique. We're going to use stoichiometry, and we're going to do a primary standard to determine the concentration of our sodium hydroxide, and then use the standardized sodium hydroxide to find the amount of unknown acid present. And yeah, use stoichiometry to determine that. So we're going to practice stoichiometry in lab. That's what I'm trying to tell you. Cool? All right. So anything else going on? There's a test in, not this Friday, but next Friday. And we may not get through chapter 6 at the pace I'm going, but we'll get as far as we can, and then we'll do the material up to that point. Okay? Does that sound good? Actually, we'll go pretty fast today because it's mostly definitions. Okay? And then we'll be back in the mathematics in the next lecture. Okay? Cool? All right. So definition-wise, some things that I need you to grasp or hang on to is that the energy is the capacity to do work or to heat objects. Okay? Those types of things play a role in what we're about to talk about. And I want you guys to think about heat and work as actually transferring or conversions of energy from one form to another, right? And so they're really more a transferring of that, and we can actually calculate those things, okay? For this class, we're going to focus on the heat side of it, okay? And I know this is hard work, but I'm going to ignore work quite a bit for this. Now, it's not to say that we also can't add work into the calculations, but I like to do it with just one component and in terms of the internal energy, and so it simplifies the calculations. The work side would be done the same, right? And when you take PChem, then you'll get to do both work and heat in your thermodynamics. Cool? Okay. So, energy concepts. Chemical processes, we often look at reactions, right? And the amount of heat that's generated by a reaction or removed by a reaction, changes in energy states, right? And so we calculate those and we look at that. We measure those most often by temperature, right? And so there's a physical change that we can measure. Now, I can't tell you how important this is. All right, I'm going to show a slide here in a second that's an Erlenmeyer flask, and it's going to define system and surroundings, all right? And then we have the universe that contains both the system and the surrounding. And so there's some mathematics we're going to learn related to that. But the important thing that I can't harp on more is the direction energy goes. Okay? Energy is directional. It is either coming in, which is a positive sign, or it's leaving, which is a negative sign. Okay? Well, for the system. Right? So, now what I mean by that is that when I'm doing calculations, if I don't pay attention to the sign, then I'll get the wrong answer every time for a general chemistry student, right? You guys with me? But in reality, you're trying to keep track of which direction it's going, and the sign is how you do that. So it's really helpful to actually pay attention, to learn the language of those types of things, so then the mathematics set up easier, right? So now, we can both calculate energies from table values, and then we can actually measure those in experiments such as calorimetry. Okay? So you guys, have you ever heard of a calorimeter? Right? Now, that measures calories, right? And in fact, anymore, the appropriate unit would be joules. Okay? but the technique was developed on the unit calorie, so it still holds that name. All right, potential energy, right? So what is potential energy? It's stored energy, right? And can just even position change the potential energy? Yeah, if I move up on top of the bench, right, and so when I'm sitting, usually I jump up and down the stairs, but because of COVID, I'm in front of the class, right? So here we go, I'll get on this side. And so do I have a higher potential energy than I did when I was on the floor? Yeah, and how do I release that? I jump, right? You guys with me? Yeah. And so there's some things that happen when I jump, right? I become kinetic, I'm moving, right? There's an abrupt stop at the end. And so what are some other changes that happened with the abrupt stop? Where did the energy go? Converted forms. Wasn't there a little bit of heat, right, generated as my feet hit the floor? Some of it went there. My muscles absorbed that, right? And so there was a change in them. They probably changed temperature too. They also changed position, right? You guys with me? And so there's things, mechanical movement that occurs, right, in that sense. But what about in chemicals? Is there potential energy in chemicals? What if I have a big tank of propane? Is there any energy in that propane? Can I take that? How do I get that energy out? What do I do? Can I combust it? Yeah, and so well, wait a minute, where's that energy stored in the molecule? In the bonds, right? And so there's stored our potential energy in bonds, and as I break bonds and then reform bonds to change the chemicals in the reaction, then I can lose heat, right? I can gain the energy for some other purpose, to heat my home, which seems like an important thing on a day like today, right? A little bit chilly outside with the rain. Yeah? So anyway, so think about it in that fashion, that atoms and molecules not only can move, all right, the kinetic energy in that way, or potential energy, but that we have chemical energy that can be obtained from looking at bonds, right? There's a potential there. So we're going to look at all of those things, and we're going to look at it. And first thing we need is some energy units, right? And so a joule, all right, that's the SI unit. And for any measurement of energy, then the modern reporting should be done in joules. Now, we still use calories, okay? Where do we use calories? Every day. Anybody monitor their diet at all? On every package label, how is the energy reported in the United States? Calories. If you go elsewhere in the world, do they have calories on the labels? If you go to Europe, for example? No. What do they have? Joules. Okay? So be aware of that we're slow to change here. Okay? Even though the scientific world is using joule, we're still resistant and we stay with calorie. I'm kind of still the proponent that we switch to, right, the metric system, and we switch to the SI units, and so then there's no confusion, right? I can't remember the mission now, but I remember reading an article describing NASA's missing of a target, right? Because one group was working in miles and the other one was working in kilometers. That's a big difference, isn't it? And so when you put that together and you combine the two groups, then and you didn't pay attention to units, that's why I'm such a stickler about writing units on your calculations, right? Because it does make a difference. All right? So a conversion that I remember, because also we're going to look at specific heats, and so specific heats are the amount of heat that it takes to raise 1 gram of material 1 degree C. And for liquid water, right, which is something that's very common and we use in a lot of experiments, the specific heat is 1 calorie per gram per degree C. Or if I do it in joules, can you guys do that conversion for me? What would it be? 4.184 joules per gram per degree C. Okay, so we'll see that in a minute. But that conversion sticks because of that unit that's used so often in things like calorimetry. And we'll talk about why and those things here in a little bit. And then there's a big C and little c, right? You guys realize that. A little c is the experimental calorie. And if I capitalize the C, then that's a food calorie. Okay, or dietary calorie, right? Or a kilocalorie of experimental calories. 1,000 of those. Cool? So if I have a food measurement for calories and it's 10 calories, that's 10 food calories. And, well, what would that be in little calories? 10,000. Yeah, experimental calories. So just be aware of that. All right. So these conversions are here, and I think you guys are pretty good at conversions now, and so you guys can work between those units. Cool? In fact, Sapling's going to have you do that a little bit because Sapling loves to do that. All right? Make you change units 3 times and then do the calculation. Cool? Yeah. All right. Just a reminder of a couple things that make this study possible, right, to understand thermodynamics. One is the law of conservation of energy, all right? And so energy can either be created or destroyed, and a normal process, total amount of energy in the universe is constant, right? And energy can be transformed from one form to another. And so knowing this, accepting this to be a truth, allows us to do what we're about to do. Okay, you guys with me? So this is just a reminder. And the other thing that I want to talk about is that, well, some of that came from the first law of thermodynamics, didn't it? The total amount of energy in the universe is constant. And then the amount of heat transferred into a system plus the amount of work done on the system must result in a corresponding increase of the internal energy of the system. Okay? So if I do work on a system and I transfer heat into a system, then the internal energy has to change. If I remove heat from a system and I remove work from it, what do you have to do? The internal energy would go down, wouldn't it? Okay, so from that perspective, then we're going to track those changes. Here's some more language. And so the system, and then the surroundings, and then the universe. Okay, and so the system is that part of the universe that's under study. Now, I want you guys to be cautious here. How many engineering students do I have in here? All right. Engineering and science sometimes flip things, where you're using the system to heat the surroundings. And so the sign change in text and those types of things may go the other direction. I'm just warning you, because I've witnessed that in graduate school when I was doing the thermodynamics on gasification processes. And so I was confused because the signs were all backwards, right? But they were talking about what was being done with it, and we were talking about the system itself. Does that make sense? Yeah. And so the sign flips in that case. So direction becomes important again, right? And so knowing which direction you're looking at, and that's just an understanding of what you're doing and that idea. And so anyway, system and surroundings. And so in a chemistry standpoint, this is it, right? So we have something that we're studying, and it's a test tube or an Erlenmeyer flask, and so if I make this my system of study, right, then I can look at what occurs there. Now this system, if you notice, is not stoppered, right? There's no physical thing that's going to happen, right, that's going to affect it. And so when I'm studying something like this, then what happens? No work is done. Okay? And so when I talk about ignoring work, right, then for much of chemistry, we can ignore it because we work in open top vessels, and the effect of a small volume change on the surroundings is insignificant, right? Not really work done. Cool? So then we can do everything based on that idea that the system changes from heat. So we have the system and the surroundings, and then everything that encompasses both of those is the universe. Cool? Now, there's some math that we're going to learn to talk about, but the first thing that I want to talk about is the sign, right? When our energy leaves the system, right, the sign's going to be negative, okay? Because we're accounting for what? The system, right? And if energy goes in, what's the sign going to be? It's going to be positive, right? And so, now, think about it from the opposite perspective. If, maybe I should have put these on the inside, right? So if the system sign is negative, right? And this is positive when energy comes in. But what about the surroundings? It's what I was talking about a second ago, right? So if the system loses energy, the surroundings gains energy, right? Really harping on this direction thing, right? You guys with me? And so if energy leaves the surroundings and goes into the system, then, now I have a question, all right? Is the energy that the surrounding loses, right, that the systems gain, are they equal in value? Just opposite in sign? Yes. Okay? So that helps with the mathematics, doesn't it? Okay? So it's going to be equal in magnitude. Now, in fact, that's how we treat a lot of the mathematics for these thermodynamic systems. Okay? So we know we may not be able to find it for one, but if we can find it for the other, then the opposite sign, right? You guys with me? For whatever that may be. And so we'll use that philosophy to solve some math problems, okay? Where we can not directly measure the amount of heat from a burned potato chip, right? But we can use the potato chip to change the temperature of water. We know the heat capacity of the water, right? And we know the temperature change of the water. And we know the mass of the water. And if I know those things, then I can calculate the amount of heat that it took to change the temperature of water that many degrees from its starting point to its final point. And then that means that the chip had to give that much energy, right? You guys with me? And we're going to show this in slides. This is a preview. But the chip's energy is the opposite sign because it let the energy go to put into the water, right? Cool? All right, so we're going to use that strategy to solve some things. This is just showing a diver on the board. It's showing he has a higher potential energy, and his potential energy changes as he goes off of the board. And things that happen is the water level, if it's a small pool, will change significantly. If it's a large pool, would we even notice it? No. Okay? So that makes a difference. But then also be aware that as he's moving, there's friction, and so there's a change in temperature. And so the water, now if it's a large body of water, would you be able to measure the temperature change from one person diving in? Even thousands in a day. Public swimming pool? No, probably not. You guys with me? So depending on what we're looking at, sometimes we can't calculate for the surroundings in the same way we do for the system because its change is not significant. Hot coffee, right? Insulated container. Does this coffee change the room temperature? No, because there's not enough molecules here to do that, right? Take a lot of coffee to warm this room, right? Now, what about you guys? Are you warming this room right now? Yeah, you know this room is one of the warmer rooms in the building, in my opinion, other than my office where I have a space heater going. So, And then we have some in the lab too, it's getting better. So anyway, if I'm looking, then the change in energy, right, for this is energy final minus energy initial, okay? And so that would be the change in energy, and that's the energy that's released from the die, okay? In physics, you guys have calculated these if you've taken that course, and we'll do a little bit of that in here, okay? We'll do a lot more of it in physics and chemistry. All right, so a couple more reminders. I want to go back to a couple topics. One is thermal energy, right? We have helium atoms up there, and you guys see the motion that's represented by the cartoon? The movement. So, is that energy? It is, isn't it? The movement of those, they have a kinetic energy. They're also, well, helium atoms, their electrons are probably vibrating, right? Unless they're what temperature? 0 degrees Kelvin, which is the absolute zero, and kinetic energy stops at that point. So anything above that, we're going to be having some movement. You guys with me? Okay, so, and in fact, then there is the kinetic molecular theory, which we posted before, right? We've talked about this. We talked about gas particles are in constant random motion. They collide, transfer their energy, and they don't give away their energy to the wall. And most volume of gas is an empty space. The particles take up very little volume, and there's no attraction between the walls and the particle. So on, right? Collisions are elastic. And when we have all of that, the kinetic energy depends on the temperature for molecules. Okay? You guys with me? And so that's something to think about as we're doing all of this in relationship to, now, this is for an ideal gas, and real gases, when we start looking at these things, then we have to start doing some correction, okay? Because there is some attractiveness, and depending on temperature, there's a lot more attractiveness. In fact, some gases, well, all gases liquefy before they get to absolute zero, right? So they're no longer gases. And so those things really do happen, and so we have to do correction for real world things. But this is a nice place to start. And so then from that to step off to this idea that all matter has thermal energy, okay? All matter has thermal energy. As the temperature increases, the thermal energy goes up, right? Energy is conserved. What does that mean? What does it mean to conserve energy? The total amount of energy in the universe is constant, isn't it? And so, in some fashion or another, it can go from a higher form to what we consider a lower form, right, where I have more organized in chemical bonds, and I break those bonds and make more gas. It becomes more random, and so there's an entropic change, for example, and when that happens, then heat is released, and that's thermodynamically favorable, right? And so anyway, but it's conserved. We can measure that. And so anyway, energy is neither created nor destroyed, and the total energy in the universe is constant, right? And so energy can be converted from one form to another. Now this is right out of the laws, isn't it? So to do this, I'm kind of beating on those a little bit. And so I'll probably ask you a couple of those on the test, right? Because they're significant in this, and so just to let you know that. All right? And then the last part, which is what we're really going to look at first, okay? Energy can be transferred from one substance to another, right? You guys with me? So I think of it, my brain jumped automatically. How many people, when you left the door open at your house, and I find myself as a dad doing the same thing my dad did, and the question is, were you born in a barn? Okay, and you're letting all my cold air out.
We're not heating the outside.
We're not heating the outside. Oh, that's good. I like that. We're not heating the outside nor cooling it, right?
Trying to air condition the whole neighborhood.
Are we trying to? Okay, so you guys have all been there and seen that. And so my mind, when I'm reading this and thinking about the processes that we're going to do, then we're looking at that heat exchange. Okay, and note that heat always goes from hot to cold when it transfers, okay? And so that it has a direction in which it travels. So if you're letting all the cold air out, right, Note that that's not true, you're letting the hot air in. Yeah, maybe a nuance that's not really applicable, but it's kind of a joke to me, okay? So, but I always go there. So, when I have energy transfer, right, two different samples, and I put them in contact with each other, right? One sample transfers it to the other by heating it, okay? Now, the one that's doing the heating is losing its energy, right? The same amount it gives to the other object, and so mathematically we can track that, right? If I let them sit till equilibrium, will both objects have the same temperature? Yes, all right? And so it occurs until they're both at the same temperature. This allows some math to happen, okay? Now, right now I want you guys to think about this and draw a picture on the nanoscale. That means draw some atoms, and I want you to show the cold object and the hot object, and then the two objects when they've come to equilibrium. Your mental picture of that. Anybody want to do it on the board?
No.
So if they're two solid objects, right, the atoms are fixed. What's the motion in those atoms, though? Are they vibrating? Yeah, they're vibrating, and so the cold one would be vibrating less than the hotter one. And then after they come to equilibrium, kind of. If they were the same material, they would be, yeah. But that'd be the way I draw the concept picture. Yeah. This isn't it. This is a different picture. This is showing a piece of cold metal and a piece of hot metal. So we can actually look at it to see if we're kind of in the right idea, right? I'll let you finish drawing though. Anybody still drawing? Made a cool picture. I look at it, your cold object, right, would have less motion than your hot object, as we were describing, right? And so it would be the opposite for the hot object would even have more motion than it would go to the colder object, right? And so that transfer of energy occurred, and we would have, well, in fact, we can determine based on mass, okay, of material, mass of material, the specific heat of the material, and the starting temperature, initial temperature, we can determine the final temperature of both objects. All right, let's learn how to do that. All right, oh, there's a coffee cup. Where does the heat in my cup go to? The surroundings? Yeah. All right, initial state of energy higher than the final state of energy. And so there's a heat change associated with that. If I know the mass of the coffee and I know the specific heat of the coffee, which would be very close to that of water, right? Then I can calculate a specific amount of heat that left from my cup, right? I should write the equation on the board. We're going to get there sooner or later. All right? Q, heat, okay, equals MC delta T, where delta T equals temperature temperature final minus temperature initial. Okay? Heat mass specific heat and change in temperature. Okay? So this is an equation that we can look at the amount of heat that was transferred to the surroundings. Now, you say, okay, why are we doing this? Well, think about it from an engineering perspective. If I need to change the temperature of an object, a system, right, and I need to know how much heat to put in, right, then I can actually calculate that before I run the experiment and know how much to have prepared. Does that make sense? Yeah.
What does that say specifically?
Specific heat, H-E-A-T. Right. We'll define those terms, okay? Before we get there, we're going to talk a little bit about internal energy and another equation, but the one we're going to use more is over there. The internal energy is the sum of individual energies of all nanoscale particles, atoms, ions, molecules in a sample. And the total internal energy of the sample depends on the temperature, the type of particles, how many of them there are, right? And don't forget kinetic energy is E equals 1/2 mv squared, right? So what is that M in that? Mass, and it's actually velocity, isn't it? Yeah. And so, I mean, that's why a big lineman usually has a better opportunity than a small lineman when they meet at the same speed, right? Because of the mass, they have more energy. All right. So when we're looking at this, then the change in energy, right, for a system, if I put in energy, right? Well, we actually defined this already, didn't we? Right? So instead of using an Erlenmeyer flask, which is what we would study with, this has got an orange box, right? But this is showing that energy goes in, so my energy goes from an initial state to a final state, right? And this is showing energy leaving, so my energy initial and energy final here. And so if I'm talking about a change in energy, right, final minus initial, then that has a sign, doesn't it? Okay? And so when energy goes in, it's positive because it increases for the system, and when energy leaves, it's negative, right, because the state of the system goes down. Yeah. So you guys starting to get, I mean, is that starting to stick? I've done it a couple times, trying to get it to stick. All right. So, some mathematical terms, another equation that we're going to look at is the internal energy of a system, right? The internal energy of a system, which is E, right? Which is harder to get the absolute energy for something, right? When we're looking at changes, then we normally look at delta E, right? You guys with me? And so that's final minus initial like we saw in the previous picture, all right? Just be aware of that. And then there's that term work. And what are we going to do with work for a lot of this? We're going to ignore it, right? Not because it's bad or anything else like that. We're just going to take that out of the statement. And so when we do that, then the change in internal energy becomes the amount of heat that moved. You guys catch that? The change in internal energy becomes the amount of heat that moves for a reaction. And we can calculate the heat with that expression. Cool? Yeah, so that's what we're trying to get to. That's where I'm going. And here's that one more time, that same picture I've got on the board. Heat transferred in and heat transferred out. Okay? Work transfer in and work transferred out in relationship to the change in the internal energy. So if we add the work term in, can we do that? Look at a piston and how it moves in relationship to the chemical reaction, and yeah, it just adds another level to the calculation, right? So, like I said, I'm going to mostly ignore that. I'm actually going to do some math with that. All right. So, Heat transfers from hot object to cool one. Energy is not lost or gained, it's transferred, it's converted from one form to another, and that's the expression that we would use to do that. Okay. So now we're ready to, I didn't think we would get this far today, but now we're about ready to step off on some calculations. Okay, so we need to do that with some more terms. I know you hate that, but we're going to calculate heating from temperature difference. We're going to do it for accompanying physical changes, okay, so reaction, and for accompanying chemical changes. And so we're going to do all of those calculations before this chapter ends. And then we're also going to do it from a table. Okay, we're going to start looking at heat in terms of, anybody ever heard of the enthalpy? All right, it's H is used for that. We usually look at a change in enthalpy, delta H. And so when no work is done, it's actually equal to Q. Okay, so that's a relationship that we're going to also utilize. So anyway, you guys have heard me talk about specific heat, right? And so specific heat of a liquid water. Now notice I put liquid in there, right? The old slide set doesn't have that, but I want to make sure that you realize that the state that the substance is in, right? If I'm liquid, I have a different heat capacity than I do when I'm a solid. And I have a different heat capacity when I'm a gas than I do when I'm a liquid or solid. Does that make sense? Right? The amount of heat that it can absorb before its temperature changes is different for the state that I'm in, or the phase that I'm in. All right, so for liquid water, it's 4.184 joules per degree C, or if I'm working in calories, okay, if I'm working in calories, it's 1 calorie per gram per degree C. Cool? So that's a definition. This is a list of heat capacities. Now I want you guys to start doing some comparison, right? And if I'm looking at the metals up here, all right, and then I start comparing them to compounds, what do I see? Are the compounds higher or lower than the metals? They're higher. So it takes less heat to raise the temperature of metal, right, than it does many compounds. In fact, liquid water and ammonia right here, those have some of the highest known heat capacities as compounds, right? Now, this is actually part of our climate that we've been talking about in energy too, because of water's nature, right? Its polar nature, it has a really high specific heat or heat capacity, okay? And so in that, then it takes a whole bunch of energy to change the temperature of it. Whole bunch of energy. And so, well, in fact, it helps to keep the temperature of the planet moderated. Right? And then in addition to that, the phase change that occurs, also there's some energy involved with that. And when it changes from liquid to gas, right? Energy has to be put into the water to do that. And so when that happens, the temperature's not changing. The opposite of that, when it goes from the gas phase back to the liquid phase during the night, that heat is then released into the atmosphere around it, and so it helps to moderate that temperature, especially when there's a lot of water in the atmosphere. And that's why when it's really wet outside, the temperature from night to day doesn't change near as much as it does when you're in a desert and there's no water present. Okay, so that's connected to this in that relationship, right? And so anyway, now if you move down here, then you find here's water ice, it's 2.06 versus the 4.184 joules per gram per degree C, right? And so the solid water doesn't have as high a heat capacity as the liquid. You guys with me? So it takes less heat to change the temperature of ice than it does to change the temperature of liquid water. All right? Now, I have a question. What is the temperature of ice? For pure water, it's less than 32 degrees Fahrenheit or 0 degrees, or it's at 0 degrees Celsius or 32 degrees Fahrenheit. But if I set my freezer to negative 20 degrees, right, then the ice starts at negative 20, right? And so then if I take that piece of ice and I put it out here on the counter, what happens? It first warms to what? To 32 degrees, then what happens? Then it melts, and the system would stay at 32 degrees until all of the ice is melted, right? And then once it melts, then it would start equilibrating. It's still equilibrating with the room, but it would start changing temperature again as a liquid, right? And in fact, we'll look at those heating curves related to water and do some of those calculations. But anyway, so now we've got the Q, the specific heat. We already know what mass is. You guys have a good idea what temperature is, so we can do some math. Exciting, right? Sure. Yeah, well, let's talk about one more unit. Don't forget, we can do things in grams, but can we also do them in moles? Yeah, and so pay attention that it's molar heat capacity or specific heat, okay? So those are two different units, but they do the same calculation, and so Sapling will throw some of those at you, okay? So make sure that you're using the right specific heat or molar heat, depending on the circumstance, okay? All right, here it is. The official slide. We're there. You guys already have it, but does that look very hard? No, it's pretty basic algebra, okay? So it's just knowing what to put in there. All right. Plotted graphs are heat absorbed versus temperature for two systems, okay? The same amount of heat, or the heating rate is the same for both of the systems. Which one of those has the lower heat capacity? Which of those has the higher heat capacity? I always have to rotate the graph. Which one has the highest temperature? B. So for the same amount of heat put in, the temperature changes more for B than A. So which one has the higher heat capacity? Heat capacity is defined as the amount of energy that it takes to change the temperature by 1 degree C. So one of those has a higher capacity. A does, right? Because the temperature didn't change as much for A or the amount of heat absorbed. Okay? Is with me? Yeah. Trying to put that concept in there. All right, here we go. Cold iron, hot iron, cold iron. Okay? Hot iron, cold iron. We put it in water to cool it down. Where does the heat from the iron go? Into the water, right? Until they reach equilibrium. So Q lost by the iron, right, equals the amount of heat gained by the water, right? But it's going to be the opposite sign. You guys catch that? So let's write that on the board. Let's do this. Add B. what I'm doing is I'm defining it for a calculation that's coming up, right? And I'm saying that I have a hot piece of iron and I drop it into a bucket of water, right? You guys with me? And the temperature, the heat from the metal goes into the water. Cool? All right? And so in that case, the Q is the Q lost is the heat lost by the iron, right? And the Q gained is the heat that went into the water to make the temperature change. Cool? How many people have done this in a farm shop after they have welded or used a cutting torch? Yeah. You just have a tin can full of water there, you drop it in there so you can do something with that, right? And so anyway. Now if that's the case, then Q equals MC delta T, right? Q equals MC delta T, and so we're going to have, well, go ahead and expand that for the water and for the iron, right? You go ahead and expand that for the water and the iron, and so
There should be an E on
oh yeah. Yeah, I just left it off. It's totally an accident. It's not chlorine. Dr. Eason's favorite element. All right, so remember the delta T is temperature, final temperature minus initial temperature. We're going to use that. So, all right. Piece of metal heated and inflamed to a certain temperature. Hot metal is then placed in a beaker of cool water, and so the water gains the energy, and the metal loses the energy, same amount, however you want to say that. And so we can do this for this question right here. Okay? So, what's the mass of the iron? I should let you read the question real quick. 100 grams of iron is placed at 100 degrees C, is placed in 200 grams of water at 20 degrees C in an insulated container. What will the temperature, delta, or degrees Celsius, the iron and water be when both are at the same temperature? Okay. Then it gives the two specific heats, right? Specific heat capacities. Or gives one of them. We already know the other one. It's in calories. So. All right. So what was the mass of the iron? 100 degrees C. And this is going to be multiplied times the specific heat. 0.106 calories per gram degrees C. Right? And then that's going to be multiplied times delta T, which I'm going to go ahead and put in as T final. That's what we're looking for, isn't it? That's our X, if you want to call it that algebraically. Minus the initial temperature, 100 degrees C. Cool? Yeah.
Why did you put 100 degrees Celsius at the beginning?
Oh, I meant to put grams, because I literally wrote degrees C because I was working towards that temperature term, and my brain was ahead of, my hand was ahead of my brain. My brain was ahead of my hand, or it was an error. I was just seeing if you're paying attention. All right, and so this is our term for water, right? And so then this is going to equal negative, right? And what's the mass of the water? 200 grams.
Now, is that would be water or FD?
Oh, this would be FE. Yeah, golly. I'm really not connected right now. All right? It happened. 200 grams, and then the specific heat of water is what in calories? No, that's actually in joules, okay? It's one, yep.
How do you know
I have it memorized, but I would give that to you on the test. Yeah. So, and then times T final minus T initial, T final times what's the temperature? 20 degrees C. And so at this point, this is the water term, right? And algebraically, I solve for T final. Okay? I'm out of time, so we don't have time to finish it today. But that's the setup, and we'll pick this up right here and reset it up on Friday. Okay? We'll reset it up on Friday. If you can't stand it and you want to solve it, the solution is there.